Well, now, in the next part of electromagnetic induction, our discussion will be regarding the generators as well as the transformer. However, you can remember that both devices are working on the principle of electromagnetic induction. Moreover, in both the cases, Lenz's law will be adopted, and as I am repeating again and again, the Lenz's law states that the direction of induced current is such that it opposes the cause which produces it. Now, first of all, we come towards generator or dynamo. Whether we speak generator or dynamo, the function is the same one. So, generator is basically a device which converts mechanical energy into electrical energy. And working of generators is based on the principle of electromagnetic induction. As I have explained earlier, that electromagnetic induction is a phenomenon in which, due to change in flux, there is formation of induced current or induced EMF. So, generator or dynamo will operate on the principle of electromagnetic induction, that is, by changing magnetic flux, induced EMF or induced current will be generated. So, basically, the purpose of generator or dynamo is that is converting mechanical energy into electrical energy. Now, generators will be of two types. One is called the AC generator, the other is called the DC generator. In case of AC generator, if the current produced by generator is alternating, then the generator is called AC generator. The point to remember is that the alternating current is in the form of sine graph or cosine graph. When we use the term cosine graph, there will be some path difference or phase difference in the voltage and current. So, alternating current has tendency, that is moving in the form of sine curve. One complete cycle is completed in 1 over 50 seconds, and the frequency of alternating current is generally 50 cycles per second. This frequency varies from country to country. In India, this frequency is kept at 50 cycles per second with the operating voltage of 220 volts. Now, in DC generator, if the current is produced by the generator, then that is direct current, that is unidirectional current. It moves in the form of only crests. Generator consists of the following parts. There are four parts in the generator. One is armature coil, other is a magnet, the third one is slip rings, and the fourth one is the brushes. Armature basically is a soft iron core and its susceptibility is more. Susceptibility is a property of material due to which it gains magnetism easily and loses magnetism easily. Then we come to a magnet. Obviously, the magnet is a horseshoe type magnet and the pole pieces are concave. Then comes the slip rings, and slip rings are also adjusted in a particular part of the generator, and the brushes which we find will help in the change in flux. Now, in DC generator, commutator is used in place of slip rings. So, in AC generator, it is the slip rings, but in case of DC generator, it will be commutator. So, in DC generator, commutator is used in place of slip rings. In order to produce the magnetic field in a big generator, several magnetic poles are used. In these generators, the armature coils are kept stationary and magnetic pole pieces are made to rotate around the armature. Magnetic pole pieces means that magnetic poles will give rise to magnetic lines of forces. That is, they will generate magnetic flux. And whenever coil will rotate in that magnetic field, the lines of forces will be cut and induced EMF will be generated. The frequency of alternating current produced by generator of multipole is, that is given by function number of poles multiplied by rotational frequency. When we use the term rotational frequency, that is number of rotations per second divided by 2. So it will be N by 2. Capital N indicates the number of poles and the rotational frequencies indicated by small n. Now, in the diagram, you can see the first diagram, the left side diagram, that will be AC generator, and the right side diagram will be the DC generator. In DC generator, a commutator is operating, and NS is indicating the north and south pole, and brushes are indicated by particular arrow. And there will be a resistance, that is, the kinks are produced in the wire. Now, the armature coil, as shown by the direction, armature coil is moving in the clockwise direction. The coil is connected to the brushes and commutator, and it is placed between south and north pole. So, the lines of forces will move from south to north, but the magnetic field will be developed from north to south. The lines of forces are always emanated from the north pole, but it is moving in a magnet from south to north pole. So, in the DC generator, armature is indicated, armature coil, then it is commutator, the brushes, but in AC generator, instead of commutator, a slip ring is indicated. So, there is a slip ring, brushes as they are in DC generator, and south and north pole are the concave pieces, and the coil, armature coil, is again adjusted between the south and north pole, and the north pole is emanating the lines of forces. So, the point to remember is that instead of slip rings in the DC generator, a commutator is used, whereas in AC generator, slip rings will be used. The remaining working is almost the same. AC current generator is shown, and it has the different parts like magnetic poles of a horseshoe magnet. There is an armature, it's a rectangular coil, there are brushes, slip rings, and a galvanometer. Now this coil is rotating in between the poles. It is cutting magnetic lines of forces. As a result, induced current will be generated, and that induced current is indicated in galvanometer. This current is in the form of alternating current, that is in the form of crest and trough, having the time period of 1/50 seconds. So up to the time this coil will go on rotating, the current will be generated. Now, energy losses in generators will be of four different types. That is, number one is the flux leakage. So there is no control over the leakage of the number of lines of forces. Copper losses are there. Then comes eddy current losses. Eddy current losses are in the form of heat. Hysteresis losses, that is, energy of magnetic field varies. Mechanical losses, that is, rotational kinetic energy, is slightly varying. So, efficiency of generator, that is, practical efficiency of generator, is estimated by function electrical power generated by generator divided by mechanical energy given to generator. So, practical efficiency of big generators are nearly 92% to 95%. So, it is not a constant value because electrical power or mechanical energy, they are never constant, they are variable. Hence, the practical efficiency varies from minimum 92% to maximum 95%. They are not 100% because of flux leakages, the copper losses, the eddy currents losses, the hysteresis losses, and mechanical losses. Now comes the motor. So motor has an operation which is inverse of the generator. So in case of motor, it converts electrical energy into mechanical energy. So electrical work will be adopted, and that is converted into mechanical energy. Mechanical energy means mechanical work done. So when current carrying conductor is placed in magnetic field, a couple acts on it which makes the coil to rotate. So the point to remember is that when we place a coil in magnetic field, then the opposite ends of the coil will experience force, and due to equal and opposite forces, we find that the coil will begin to rotate, couple will be generated. So you will remember that couple or the movement of couple is the product of force and perpendicular distance. Then we come towards electric motors are of two types. So electric motors, we classify them into two types. One is alternating current motor, the other is direct current motor. Alternating means that Current is variable, that is, direction changes periodically. Direct current means that direction is always same. DC motor consists of the following parts. The parts are again the same: armature, the magnet, and instead of slip rings, it will be commutator. And the last one like brushes.